In the last episode of this devlog series for Redacted OS, I explained how I set up memory mapping using something called the MMU. That way we can set up certain memory to be used only by the kernel and certain memory to be used by processes. And I even talked about what can happen when those rules aren't followed. But today we're going to talk more about these processes. Specifically, what exactly is a process in the first place? Well, simply put, a process is a computer program, or more specifically, an instance of a computer program. That is, the computer program when it's actually loaded into memory. And this is actually an important distinction. Let's take this simple program as an example. It creates a global variable called I, and then the program actually increments it every time it runs. So let's imagine we have two instances of that, process 1 and process 2. Well, if they both share the same code and the same data, they both will call that increment. And that means that our variable will increment 2 times instead of just 1, because they will share the same data. This is definitely not something that we want to have happen. And that's why we want to instance these and have them have their own data and code. So let's take a simple example process. It's going to be similar to what I just showed, but it's going to look a little something like this. It's going to have a simple counter declared as a global variable, and then a main function called process.main that just has an infinite loop in it and then prints a string. In this case, just the word process and then the value of the counter, which it then increments. So it's a pretty simple process. We just load it into memory, and then what do? Do we just call its main function? Well, not really. This would have some major issues. The first one is that it is not instanced. So we would have the problem that I mentioned before when we increment counter. Also, we're just blindly trusting the process. We're not really doing anything to check that it isn't trying to do anything malicious, or to introduce all the protections that we talked about in the last episode. And finally, there's not really a way to do anything besides run the process at this point. It's an infinite loop, which means it never exits. And now we're just stuck running it forever if we just call its main function. So let's solve these issues one by one, starting with the instancing. So our program can look a little something like this before we instantiate it. It is divided into sections, which are declared in the linker, and we talked about the linker a little bit in the first episode. It has a text section, which contains the actual code, an RO data or read-only data section, which can include things like strings or just in general variables that are meant to be read but not written. And then data, which is read and write data. This can include things like our counter. Global variables that are initialized. There's a few more sections that I'm just ignoring for brevity here. This is pretty much enough to understand how our program is structured. So we just make a copy of that and put it in memory somewhere, right? Well, normally, yes, this would be enough to instantiate a copy of the process, but there's a problem. I haven't really talked about a file system. We're not really loading any files that contain all this information. And what we're doing right now is actually including it in the memory itself. That is to say, our processes are compiled and included in the kernel code itself. So this is just a temporary solution, and we will see how to do it properly by the end of this video, but for the time being, this is how things are. And this introduces one major problem. You may remember that our code calls a printf function, and that printf function is also somewhere in memory. So in order to call that function, the code needs to be able to know where that function is. And in assembly, this looks a little something like this, blprintf. BL simply stands for branch link, and it's essentially a function call. But when this actually gets translated to binary, we can't just write printf, we have to know the address where printf is. And specifically, the way that the compiler does that is by not writing the address of printf entirely, but rather its offset compared to the code that's calling it. In this case, I'm simplifying things a lot, I'm just writing -2. So now, when we copy the code, it's going to try to move 2 positions behind, and there's not really any data there. Or even worse, there can actually be other data there, which can be a security vulnerability, but also just not a very good thing in general, because the code is not doing what it's supposed to do. So, long story short, we need to do some kind of translation in order to properly point to the printf function. And in order to do this, what we're going to do is we're going to calculate where the original instruction was and what the offset that pointed to printf is. That gives us the address where printf is located. Then we can just get the current location of the new instruction where we've copied the instruction that we're trying to translate. And by comparing that to the printf address, we can get the new offset. And just like that, we're able to copy our code in a way that jumps to the correct place to call printf. And again, this relocation code only matters because our current code for the processes is being loaded alongside the kernel. Eventually, we will load it from disk, and this won't be necessary anymore, although it probably will still be necessary for dynamic linking in the future, but we're not talking about any of that today, so let's consider this to be a little bit of a hack for the time being. Of course, we're going to want to remove this limitation where the process has to be compiled and shipped with the kernel, because otherwise we're not going to be able to have any third-party processes, and updating processes means updating the entire kernel, which is not ideal. But we'll get to that eventually. We have two more issues that I mentioned to talk about. The first one is the fact that right now our kernel instantiates the process and then calls it with its main function. And then it can't really do anything else. So the solution to this is scheduling. Essentially, our kernel will create a scheduler. The scheduler will be in charge of creating the processes, and when the kernel activates it, it will select which process to run that process, and then switch to another process. That way, it will keep things going so that all processes can run, and also anything else that our operating system needs to take care of can also happen while processes are running. But how are we going to make this scheduler? Well, we're going to rely on interrupts. Essentially, we're going to receive a signal every once in a while that tells us that we need to switch processes. The type of scheduler that we're going to be using is called a round-robin scheduler. It's one where processes are run sequentially and all run for the same time. But in order to do this, we need interrupts. Let's talk about what interrupts are. Now, I'm not going to sit here and state the obvious on how interrupts interrupt the execution of the current instruction in order to execute a different one, and then allows us to optionally return to the previous instruction afterwards, except I just did that. But essentially, let's imagine that our CPU is currently running one of the processes, and it receives a signal from somewhere called an interrupt. That signal will be handled by the vector table that we defined in the previous episode, which we'll call a handler. And in that handler, we can have the scheduler code that switches to the next process. Specifically, we're going to be using a timer interrupt, simply an interrupt that runs after a certain amount of time. Essentially, we're going to tell this timer interrupt when we expect it to fire an interrupt, and when that amount of time has passed, the interrupt will fire and we will be able to switch processes. If we do this every few milliseconds, then we can switch between processes and have multitasking. And that way we won't have the problem where our process runs indefinitely and our system is completely blocked because the process is running. Okay, so how do we set up these interrupts? Well, we're going to use something called the GIC, or the Generic Interrupt Controller. Now, in order to set up this controller, we're going to need to access two registers, the distributor and the interface for each CPU core. Now, the distributor is the one in charge for actually receiving and setting up all the interrupts, but modern-day CPUs actually have multiple cores. All of these cores essentially act as their own little CPU, working independently from each other. And this means that each of them needs to be able to receive an interrupt. So through the interface, we can set up interrupts for a specific CPU core. However, for the time being, we're only going to be using one core. Honestly, this whole thing was already difficult enough to set up without having to deal with multiple cores. If I had to do that, I would probably go crazy. So I will get to it eventually, but not just yet. Now, in order to work with these two registers, first off, we need to disable them. I know it can seem counterintuitive to disable them when what we're trying to do is enable them, but we're going to have to disable them, configure them, and then re-enable them again. So we're going to disable them by writing a 0 to the register that is, for now, hard-coded. After that, we have to decide which interrupt we're trying to configure. Essentially, you can have multiple interrupts, and they have an identifier called an IRQ line. IRQ stands for interrupt request. In this case, we're going to use 30 for our identifier, which I think is just a hard-coded IRQ line for timer interrupts on ARM. So whenever I refer to IRQ line or IRQ, this is what I'm talking about. Now, the first thing we're going to have to do is enable the IRQ line. We're going to do that at offset 0x100 of the distributor. There, we're going to have to determine which register and which bit inside that register corresponds to the IRQ line that we have set up. The GIC in its current version uses 32-bit registers, and in each of those registers, one bit represents one line. So we take our line number and we divide that by 32 in order to find which register the line is located into. In this case, it's going to be the first one because it's 30. And then because we're working with 32 bits, we have to multiply this value by 4. Once we found the correct register, we need to find which bit to write into. And we're going to do that with modulo 32 of the IRQ line. Now, modulo is just the remainder of a division. We're going to use that and we're going to perform a binary shift of the number 1. Essentially, we're going to write a 1 at the bit specified by the remainder of the division of IRQ and 32. So long story short, we are going to divide the number of the IRQ line by 32. We're going to take the result of that to decide which register we need to write to, and the remainder of that division to know which bit to write into inside the register. After that, we have to set a priority for the IRQ line, and we are going to do that by writing to offset 0x400 of the distributor plus the IRQ number. Here we're going to write 0x80, which is a high priority. Priorities can technically be used to filter out low priority interrupts in specific times, but from what I've seen, it's okay to just have all interrupts come through or all interrupts masked. Then we're going to go to offset 0x800 plus the IRQ line, and here we're going to specify which CPU core we are targeting with this interrupt. Like I said before, the CPU uses different cores which are independent from each other and can receive interrupts independently from each other. In this case, we're only targeting the first one, so we're going to write a 0 for the CPU core. Finally, we're going to go to offset 0xC00 plus 4 times the IRQ divided by 16. Because this time we're going to be working with 2-bit values instead of just 1. It's a similar operation, similar situation to the first register we wrote into, but again, we're working with 2 bits, so this time we're dividing by 16, not 32. And this is how we're going to trigger the interrupt. In this case, we're writing a 2, which stands for edge interrupt. Essentially, the interrupt gets triggered when its value goes from a 0 to a 1. So again, we're going to divide our IRQ line by 16, and we're going to take the result of that to know which register to write into, and the remainder of that to know which 2 bits to write into. We're done setting up the distributor, and now we have to set up the interface. In the interface, we're going to write to offset 4 to write the current priority level. In this case, we're going to write F0, and anything lower than this will come through. Again, we're not really worried about levels and priorities. Currently, all our interrupts can go through, or none of them can, depending on the situation. But in this case, we want all the interrupts to go through. Finally, we're ready to re-enable the interface and the distributor, and our interrupt should be live. Now we need to set up the timer, but just to finish this section, when we receive an interrupt, we need to acknowledge that that interrupt was received by writing the number of the IRQ line that we've just processed to offset 0x10 of the interface. That way we will indicate that our interrupt was handled and we are open to receiving more. But before we get to that point, of course, we need to actually configure the timer. So let's do that. The timer is part of the CPU, but the timer does not work with seconds as a timer normally would. Instead, it works with a frequency measured in hertz. First, we're going to need to know the frequency of the timer, which we can get from this register right here. This is a special register that the CPU holds so that we can configure the timer. Then we have to set up how much time we want to pass before the interrupt passes. We're going to do this in milliseconds because we want to have a lot of control over how quickly our processes alternate between each other. So we're going to write it in milliseconds and divide it by 1,000 to convert that to seconds. Then we're going to multiply that by the value of the frequency that we've just gotten from the timer. And we inform the timer of that by writing to this other register. So now, whenever the specified amount of milliseconds has passed, interrupt line 30 will be triggered and we will receive an interrupt, and our handler will be able to switch from the process that's currently executing to the next one. Finally, we need to enable the timer by writing a 1 to this register right here. So now we just have to decide on how fast our timer runs to alternate between processes in a way that makes them all seem like they're running at the same time, even though technically they're running sequentially one right after the other. I settled on a timer between 1 and 10 milliseconds depending on the use case because sometimes 1 can be a little bit too fast. But my current processes are not particularly complex, so 1 millisecond is doable. But now that we can have multiple processes, we have a problem. Our CPU internally looks like this. It has registers, which it uses internally to hold values for the calculations that it's currently doing in the current instructions that it's executing, and some special registers such as the program counter, which indicates which instruction is currently executing, and the stack pointer, which indicates where the stack currently is. But let's imagine we have a program that looks like this. It writes the address of printf into x0, the first register of the CPU, in order to then jump to that address and call printf. So that value is now stored in x0. The problem is, before it's able to execute the next instruction and jump to printf, an interrupt is received. We move on to the next process, which also loads something into x0, and that overrides the value for printf. And again, we receive another interrupt, go back to our first process, and we call a BLR, which is simply another branch link like before, but using a register as the value to jump to. And this time it tries to jump to the wrong address. Instead of jumping to the address of printf, it jumps to the value that was written by the other process, which is definitely going to cause issues. So what we want to do is we want to do something called context switching. Essentially, we're going to want to separate these processes' executions from each other. Each of them can have their own version of the CPU, so to speak. And that way, the values written by one won't override the values written by the other. What we want to do is we want to store the values of all the registers that each program is using whenever we stop executing that program, and load them whenever we start executing a program. In order to do that, somewhat in memory, we have to have a struct that looks a little something like this. Now, there's a lot of values in this one, but honestly, we're not going to look at most of them. They are important and we will look at them eventually, but for the time being, we only want to look at the first three. The first one, which I called regs, is simply all the registers from x0 to x30, all the registers that the CPU could be using. And then the current value of the stack pointer and the program counter. Whenever we're executing a process and we want to jump from that process to another one, we're going to store the status of that process into this structure. And then whenever we return to that process, we're going to read it from this structure, put it back in the CPU, and continue running the process. The idea is to make sure that the process doesn't even realize that it stopped executing. It just continues executing without ever realizing that something else happened in between. But there are some issues with this. The main one, we need to know how to reach the structure. We need to have a pointer to it somewhere. And because of the way that the C calling convention works, that pointer is stored in x0, which means just by saving the values, we're overriding one of the values that we're saving, which is definitely not ideal. And also, we need to somehow calculate this pointer, and that could also potentially alter some other register values. So to fix this issue, what we're going to do is we're going to write the values of the registers that could be potentially overwritten into other registers that we don't care about, or at least we hope that they're not being used. In this case, I'm writing it as x15, x14, and x13 for x0, x1, and x2. But if you look at the code, it's probably different. This is because I started storing different values at different times, and I'm also storing some other values besides just these three registers, so it's not exactly in order, but just to show it in a neat way here, I'm using sequential numbers. So the second we start context switching, the second we receive that interrupt that tells us that our process needs to stop running and we need to switch to the next one, the first thing we're going to do is store the values of the important registers that could be getting overwritten into some other registers that we assume are going to be safe and we're not going to overwrite. We can use registers between x10 and x18 to do this. I used to do it between x10 and x19, but as it turns out, x19 is being used by C++, so I couldn't use that one. So now we can safely write the values of all our registers, the stack pointer and the program counter, into the structure and then load them back. And of course move x15 back into x0 and so on to restore the process. But there is one more thing that we want to look into. The process uses a stack. And our context switching code probably also uses a stack. If we don't change which stack is being used, we're using the process's own stack, which can definitely lead to some issues. So what we're going to do is we're going to have a separate stack for the kernel. We're going to use that one instead. And whenever we're context switching, one of the first things we're going to do is we're going to switch from the process stack to the kernel stack. This actually was leading to issues in which the process was able to read the kernel stack, which is essentially kernel memory, so this is not something you want to have. So now we're able to switch between processes and even store their current state in order to have them switch between them seamlessly without losing or corrupting or overriding any data. But there is one more thing that's pretty important to processes, and that's the heap. This is one of those values that I mentioned was there, but we're not really going to look at. Maybe I lied a little bit. Now, the code for our process, the data for our process, and even the stack for our process are actually already set up. So we have the code, the global variables, and even local variables. But what about other variables, such as, for example, things that you allocate using the malloc function or a new operator in C++, and values whose exact size is not known ahead of time, but only at runtime? Well, that's what a heap is for. The heap is simply a special bit of memory that can grow or shrink depending on the program's needs that can store dynamically allocated data. And again, functions like malloc in C or new in C++ use the heap. So let's talk a little bit about how the heap is designed. Essentially, we're going to save some registers in memory. In those registers, we're going to decide which parts of memory are currently being used and which ones are not. The used ones, we write a 1 to them, and the 0, we write a 0 to them. And that way we can know how much memory we have free on our system and how much memory is being used. Wait. You didn't think we were actually talking about heap design, right? Oh, no. This is another allocator. That's right. We're talking about another allocator. What's that? The third one? The fourth one? Technically, I wrote this allocator maybe a few hours before I'm recording this video, so there's another allocator that came before this one that I'm not even going to talk about. But yeah, I think this operating system has had a lot of allocators. So our allocator is going to help us to set up process memory, the heap, the stack, and anything else that we need in order to instantiate our processes. But there is one problem with this. Each bit represents one page of memory, which I've defined to be 4 kilobytes. Essentially, each bit represents 4 kilobytes of real memory, and we can just allocate or free pages. But that means that every time a process wants to allocate even just one bit, the kernel will allocate an entire page. So what if we actually just want to allocate one bit? This is very inefficient. Well, guess what? It's another allocator, baby. Okay, it's actually the same type of allocator that we used in the temporary memory in the previous episode, which is essentially just a linked list that indicates where the next free block of memory is. And this is going to be within our page allocator. So our kernel is going to allocate pages for the processes to use, and then the processes are going to be able to allocate memory within those pages using this other allocator. So a few considerations about this. First off, we can allocate entire pages directly. If the process actually needs more than 4 kilobytes of memory, or even exactly 4 kilobytes of memory, then we just allocate entire pages for it instead of going through this smaller allocator. Likewise, pages are also linked in a similar way to how blocks are linked in this allocator. That means whenever a page is full, or it still has free memory but not enough to allocate the thing that we're trying to allocate, it can link to the next free page on memory, or even create one if one doesn't exist. And that way, our heap can grow dynamically. And finally, entire pages cannot be freed at runtime when the process is running. Once a page has been allocated to a process, it stays with that process for the time being, but it can be emptied and reused by just freeing the memory that is inside that page. And then of course, when the process stops running, all of its pages are deallocated and freed up so someone else can use them. Great, but there's one more consideration we talked about before. You might remember I used the sticker, trust the process, but you should not do that. Because you know who writes processes? That's right, hackers. And you know who wants to steal your data? That's right, also hackers. Essentially, we don't want to just trust our processes blindly that they won't do anything harmful. And all those MMU protections that we set up previously, we can use them to prevent the processes from accessing memory that they're not supposed to access or doing things that they're not supposed to do. Now, this is definitely not a comprehensive list of things that we should do in order to make sure that processes cannot do something harmful. In fact, this is just one step of the many steps we should take in order to prevent processes from doing something harmful. But you know, baby steps. Again, we're going to use our MMU mappings that we created before. We're going to ensure that processes cannot access kernel memory or device memory. And we should also make sure that they can't access each other's memory, but for the time being, that's not a thing yet. The way we do that is through the current program status register, or while context switching, the saved program status register. This is a special register in the CPU that indicates various things about the current execution state of the current process. And the one thing we care about right now is the fact that it includes the privilege level. It indicates whether the current program is privileged or unprivileged. It also indicates some other things such as interrupts, so we can use it to enable and disable interrupts whenever we need to. But we don't really care about that right now. We care about the privilege level. And I don't want to go too deep into the meaning of the status register because I honestly have not needed to look at it all that much. All I know is if you write a 0 to the status register, it runs in unprivileged mode with all interrupts available, so it can receive interrupts. And if you run 205, then it runs in privileged mode with all interrupts available. So the processes that we run in unprivileged mode, we're going to call user processes. And the ones that we run in privileged mode, we're going to call kernel processes. Now, there actually is a use case in which we're going to want some processes to run with privilege. And these are specifically processes that we use to help set up the system. Essentially, the way that Redacted OS is designed is the second we enable the scheduler, Everything that happens on the system happens through processes, be them user processes that can be even third-party processes, or kernel processes, which are the privileged ones that are part of the operating system. Also, technically, some process memory is also used in order to set up the GPU and the input system, but this is a little bit of a hack right now, to be honest. I need to clean up that code a little bit, so let's just ignore it for now. Okay, so now we can actually set our process that we used before to be a user process, because just printing a value to the console does not really need privilege. But we try to do that, and this happens. The process fails. And we can use GDB to see that it fails when it tries to call printf. Wait, that's because printf is a function of the kernel. That means it's privileged. And so our process can no longer just call printf anymore. But we probably want our process to print to the console, right? So what can we do about it? Well, we're going to do something called system calls, or syscalls for short. Essentially, instead of our process calling printf, it is going to ask the kernel to call printf for it using the privilege mode that the kernel has. So we're just going to set up one route for processes to communicate with the kernel and ask it to do certain things for them. The way we do that is through an instruction that looks a little something like this, svc, which actually triggers a synchronous exception on purpose. And you might remember that in the last episode, I mentioned that sometimes we want to intentionally trigger exceptions, and this is actually done for a good thing. And syscalls is one example of that. Technically, so are interrupts. But the instruction svc with argument 3 is going to trigger an exception. If we look at the exception syndrome register for the exception, we're going to be able to identify it as an intentionally triggered exception, and we're going to be able to parse that 3 number. Then, somewhere in our handler for the synchronous exception, we're going to have a table that indicates which syscall the number corresponds to. In this case, 3 corresponds to printf. And just like that, we can create a simple way for processes to call privileged functions by asking the kernel to do it for them. That way we can have it allocate memory and free memory for us, the GPU functions that communicate directly with the device in order to draw to the screen, a sleep function which we will see in a second, the printf function that we've talked about so far. And by the way, just to differentiate the privileged version of printf and the unprivileged version that is the syscall, I've renamed the kernel one to kprintf, short for kernel printf. And finally, another syscall for halt process, which just stops the current process from running. There are a few more, but these are just good examples. But I want to focus on one specifically, and that's sleep. So there can be situations in which the process doesn't need to do anything for a certain amount of time. It's most likely waiting for something to happen or introducing an artificial delay. And rather than just wasting CPU cycles, doing nothing, waiting for enough time to have passed, we're going to call a special syscall called sleep. This syscall is going to be set up with another timer. So we mentioned before our round-robin scheduler, which has all processes in a queue waiting to be executed one right after the other, all running for the same amount of time. And we might actually change this in the future depending on design decisions that we make. We might give them priority and things like those. But for the time being, it is a round-robin system. Well, what the sleep function is going to do is it's actually going to create a new queue, which we'll call the sleep queue. When a process requests to sleep, it will be taken out of the process queue and moved into the sleep queue. Then a timer will be configured with the amount of time that the process has requested to sleep. And after the time has passed, it will move back to the process queue and execute again. But what happens if there's multiple processes that want to sleep? Do we just use multiple timers? Well, not really. We really just want to use one timer for sleep. And the way that we're going to do this is we're going to set it for the lowest time that we're waiting. When that amount of time passes and we receive the interrupt, then the process that no longer needs to wait will get moved back to the process queue. And again, we will recalculate how much time is left for the other process. We will set a new timer, and when that gets triggered, it will also be moved to the process queue. There's actually a great video about this that I stumbled upon right before I started to implement this function, and it's linked in the description if you want to check it out directly. It goes a little bit more in depth into how sleep works and how to implement it. Great. So now our processes are ready. They even have some special functions where they can run privileged code even though they are unprivileged. However, you may remember that right now our processes are loaded entirely in memory with the kernel, which again means we have to recompile the entire kernel if we want to change a process. And also, there's no way to have third-party processes. So we're going to want to move those processes out of there and instead use the disk to load them. But we haven't really used the disk before, so we're going to have to set that up. And we're going to use a device called the VirtIO BLK PCI. This is a block device, that's what BLK stands for. And it works in a similar way to how our GPU worked, because both of them are VirtIO devices over PCI. So a lot of the stuff that we talked about for that, including how to set up the device, resetting it, acknowledging it, setting up a driver for it, and discovery over PCI is exactly the same, and you can find it in the first episode of this series. But that was a GPU. This is a block device. Essentially, it can read and write data in blocks, and our disk is divided into sectors. So essentially, we'll be able to read and write blocks of memory from this disk or to this disk. And again, we're going to do that with something called virtqueues, which we talked about with the GPU, but I didn't really go too in depth into how they work. So I'm going to explain a little bit more about them. Essentially, we have a command ring. This is a piece of memory where we're going to write whatever commands we want to send to the device. Whenever we need to send a command to the device, we're going to write it to this command ring, and then we have to inform the device that we have sent a new command. We're going to do that through an available ring. Here, we're simply going to write the index of the latest command that we have written, simply telling it where to find it in the command ring. Then the device is going to be able to pick up that command, process it, and send us back a response, or at the very least, tell us that it's done working if no response is needed. It's going to do that through the used ring. It simply is used to indicate which command was just executed. That way we can make sure that all the commands that we have sent out have been acknowledged by the device and processed. And if needed, we might be able to read a response back from the device, which in the case of reading from the disk, we definitely need to do. So we can read and write blocks to the device, but what exactly are they going to look like? Well, we have to decide on a file system. We have to have some internal structure to the disk so that we can go and find processes within it and something else in the future as well, but right now it's just processes that can be loaded and executed from the disk. So I wanted to look a little something like this. We're going to have a root folder called redOS, short for redacted OS, although I may change that in the future. Then inside of it, a folder called user, which contains user processes. And then inside of that, whatever processes you want to load with a .elf extension, which again, we talked about it briefly in the last episode, and we will talk about it a little bit more here, is an executable with symbols. But before we can actually do this, we have to decide on a format for this file system. And there's a big problem with this. Even though we're making our own operating system here, we probably want to make it somewhat compatible with the major operating systems, Linux, Windows, and macOS. So at the very least, we want to be able to compile our user processes outside of the operating system because we don't even have a compiler right now, and then have it available within the operating system, which means that whatever file system we write needs to be compatible with the computer that we work on. But the problem is Linux mostly uses the ext file system, which is native to it. Windows uses the NTFS file system, which is native to Windows. And macOS uses its own native APFS. And even though we want our operating system to be compatible with all of these, none of these file systems are really all that compatible with each other's operating system, which is definitely going to be a problem. But lucky for us, there is another format that we haven't mentioned, exFAT. And this one works mostly out of the box for all three operating systems. So we should just use that, right? Easy, simple. Except it's not, because this exFAT was made by Microsoft. Wait, why is that a problem? Oh, well, I'm glad you asked. Turns out Microsoft, well, let's just put it this way, I love it with a burning passion. Their operating system, Windows, is the best one I have ever used. And yes, that actually includes my own operating system, even though it's unfinished, pretty buggy, and doesn't really have all that many features. It doesn't have spyware. So that's pretty cool. And it also doesn't charge you for that spyware. So again, pretty nice. And actually, before I started this series, I was watching another video by a YouTuber called MooKid, who was trying to make a window from scratch. And I watched this poor guy struggle with the Win32 API, which is the Windows API for syscalls, which he needed to call in order to create windows in Windows. And as I was watching it, I was just thinking, well, I may be doing like 3 times as much work as this guy is doing because I'm doing everything he's doing, plus an entire operating system around it. But at the very least, I don't have to deal with Windows or Microsoft and their awesomeness. Except now I do. Before we get to it, let me tell you what I was in for when I decided to implement exFAT. Well, exFAT has well, honestly, to call it a spec or documentation is a bit of a strong word. It has a file on GitHub, which is the entire specification for the exFAT file system. It was also released, I believe, over a decade after the actual file system was released. So for the longest time, people didn't even have this
useful
document to work off. But wait, why do you call it
useful?
Well, let me get ahead of myself and explain this to you. Obviously, we're going to want to be able to list what is in the disk. We're going to be able to see what directories and what files are contained inside of it. And that's done through entries. There are different types of entries, and they're indicated by an entry type, which is at the beginning of each data structure that indicates what entry it is. So you look at this entry type, and based on the type that it is, you parse the data as one type or another. We're going to see what all this means in a second, but it doesn't really matter right now because you would expect that at some point in the spec, they would tell you what the different entry types are and what they correspond to. This is not a thing. They just never bothered. At no point did they think, hey, if there's an entry type that people need to read in order to know which entry they're looking at, we need to tell them which entry type corresponds to which entry type, right? Except, not really. Now, logic would tell you that this is how it works, but logic doesn't run on Windows. So the solution to this is to go to OS Dev Wiki, which, by the way, amazing resource if you're doing anything OS Dev related. And here they will tell you what some of the entry types for some of the total entries are. It's really surface level and it's not even entirely accurate, but it's better than the official specification, so I guess start there. The problem is, I think the OS Dev Wiki entry for this was written before the spec was released, or it definitely wasn't updated once the spec was released, and so some parts of it are wrong. In some cases, I ran into an issue where the official specification had the information that I needed, but I didn't know how to find it. And the OS Dev Wiki didn't have it, or it was incorrect. So how did I end up finding the information that I needed? Essentially by reverse engineering it myself. By reading the raw data and interpreting it the best I could. This is not a joke. This is actually what I ended up doing. Eventually, I had enough information to decipher the ancient texts, also known as the exFAT file system specification. And from there, I was able to complete it with the data that they actually have. But it's just a very poorly written specification. Also, big tech companies have this tendency to translate everything into your native language, even if you search for it in English. And that's how I ended up with this, in which it translated FAT into Spanish. But if this isn't a perfect representation of what it's like to interact with anything done by Microsoft, I don't know what is. Okay, let's actually talk about how to implement exFAT. So at the beginning of the disk, we're going to have to read a structure that looks a little something like this. It's very big, but luckily we only care about a handful of these values. The first one we care about is the bytes per sector shift. Now this simply indicates how many bytes make up a sector of the disk, and I talked about how the disk is grouped into sectors. This simply indicates the size of each of these sectors. To be honest, I actually hard-coded this. I guess I was supposed to read it from this value, but I really didn't. I just hard-coded it to 512 bytes, which is correct, but maybe what I'm supposed to do is read this and base it off of this, which I guess I will do at some point, I don't know. Now, you'll notice that this is a uint 8. This is an 8-bit value. That cannot really represent all that many values, but it's a shift. Essentially, we're using a binary shift just like we were before. This number doesn't represent the number of bytes. It represents the offset of a 1 in a binary number, which when then interpreted as a decimal gives us the number of bytes. And this is the same as writing 2 to the power of that number, simply because each digit of binary is twice as much as the previous digit. Once we know the bytes per sector shift, or like I did, we hard-coded it, then we have how many divisions the disk has. But the exFAT file system actually uses clusters, not sectors. And a cluster is a bigger group made up of a certain amount of sectors, specified by the sectors per cluster shift, which again is a binary shift number. So that's simply going to tell us how many sectors make up one cluster, and that way we can read the disk in clusters. After that, we care about the cluster heap offset. This simply indicates where these clusters start in the disk. At the beginning of the disk, we have the structure that we're currently interpreting, and after that we have some other information that we're not looking at for the time being. So this simply indicates where the actual clusters that contain data are. And then we care about the first cluster of root directory. This indicates where the cluster is located that contains our root directory. So if we want to find user processes, we're going to have to start here and recursively work our way down until we go through the file path that we've specified before. Okay, so once we found the cluster where the root directory is found, we need to actually read it and list all the entries. And this is what the entry type thing was referring to. We're going to need to read 3 different values that look like this. The first one simply indicates that there is an entry here, and we don't really care about a lot of the values that it has, such as timestamps for the time being. We only care about the entry type, which we need to make sure it is 0x85, which again, OS Dev Wiki told me because Microsoft couldn't. Then we care about the entry count, which simply tells us how many subsequent entries besides this one we're supposed to read. And we expect this to be 2 for the other 2 structures that we're going to interpret after this one. And then we care about its flags, specifically the flag that indicates whether this is a directory or a file. After we've parsed this entry, we can look at the next one. This indicates where the data for the file is. We expect it to have entry type C0. Then it tells us the length of the file name. It doesn't actually tell us the file name, that's in the next entry. And I know that can sound stupid, but I'm going to give them the benefit of the doubt here and just assume that actually you can have different entries as the third one that defines the file name with different sizes. Could they have done it better? Probably. But I kind of understand where they were coming from in separating the length of the name and the actual name into 2 different entries. Then it tells us the file size and the cluster where we can find the file, or the first cluster, because the file could actually be so long that it takes up multiple clusters. So what we're supposed to do is go to the first cluster of this file and read all the data that is specified by valid file size. And just like that, we'll be able to read our file. But before that, we need to know that we're in the right place. And that's where the third entry comes in, the file name. Here we're going to check that entry type is C1, and then we're going to read 15 characters for the name. Now, these characters are actually in Unicode. They're in 16 bits. Whereas my system uses characters that are 8 bits. So we're going to have to convert between the 2. But really, we only just care about the first 8 bits of each character of this name, simply to make sure that it matches the path that we're looking for. So with these entries, we are able to recursively go through the directories of the path that we mentioned before, which is redos and user, and then find whichever file name entries have .elf, and those are our processes. But then we have to interpret those files by going to their first cluster and reading their data. And finally, it's time to read the elf file. So the elf file itself has a header. So we're supposed to read this structure at the beginning of the file. First, we're going to find some magic characters, which are space ELF. And if we find that, then we know we're in an elf file. Then, technically, we are supposed to look at most or all of these entries to make sure that we're reading the file correctly. But for the time being, we're only going to look at 2 of them. The program entry offset and the program header offset. The program header looks a little something like this. So we're going to go to wherever this offset is telling us within the file and read this data structure, from which again, we should probably be looking at a bunch of these values, but we're really only looking at 2. The P offset or physical offset and physical file size. This simply tells us where to start copying memory from this ELF file into our RAM so we can have our process loaded into memory. And the file size tells us how much memory to copy. So if we follow this and we copy memory based on what this tells us, then we have instantiated our program. And actually, because our program was compiled standalone away from the kernel, we no longer have to translate addresses like we were doing before. Then the program entry offset is simply going to tell us where within that copied memory we need to jump to in order to begin executing the program. Its main function, so to speak. Now, this actually does have one major limitation, and it's the fact that all the code for the process needs to be completely contained within the ELF file. So if you remember in the last episode, I mentioned that I divided my code into kernel, shared, and user folders. The user folder contains these processes, and the shared folder contains a shared library that is supposed to be loaded by the kernel but is also accessible by these processes. And that library is responsible for performing the syscalls so that the process can communicate with the kernel. So with this major limitation of everything having to be within the elf file, this means that the shared library needs to be embedded within the executable. And it's also embedded within the kernel, so we will probably have multiple copies of it in memory until we implement dynamic linking. But for the time being, this is fine. It works. So to conclude, because this video has honestly gone on for long enough, let's look at some of the processes that I have visually implemented. The first one is a loading screen. It looks a little something like this, and really it was supposed to look like circuits. I don't know if it looks like that. I don't know how to make it look like that, but this is good enough for now. And as a matter of fact, it looks like a loading screen, but it's not really loading anything. All you have to do is press one key and then it takes you to the next one, which is the login screen. So this one simply asks you for your user password. Except we don't even have a concept of a user just yet, let alone of passwords. So this is just a hard-coded string that it checks against. It shouldn't be too hard to figure out what the password is if you look at the code. And finally, we have the desktop. This is where the processes are loaded and from which you can load all of these individual processes. Now, the three processes that I'm showing here are literally just three copies of the same process, which is the default user process that I showed before. And also the layout for this launcher desktop thing is pretty much inspired by consoles, because maybe I would want to use this operating system to make my own game engine from scratch. I don't know, I haven't really decided what I'm going to be using this operating system for, but I do know that I wanted to inspire it in consoles, and specifically I took inspiration by the Wii main menu. So finally, there's our user process. The one that we looked at the beginning now has a bunch of graphic functions. Instead of just printing a simple number to the console, it now prints a string to the screen. And also still prints to the console. It doesn't really do anything for the time being, it's just there to test that all the syscalls and all the memory allocations and everything that we talked about is working correctly. Then we have another process, a state machine that controls the boot status. It essentially alternates between the loading screen, the login screen, and the desktop. It allows you to log out of the desktop back into the login screen, and it moves from the loading screen to the login, and when you get the right password, to the desktop. And finally, one that I kind of didn't want to show because it is very unfinished. I kind of haven't looked at it too much, and it's a monitor for processes. It simply tells you the current processes that are running on the system, what their flags are, so you can see the 205 here that indicates that these two are actually the last two processes that I've showed, and they have flags 205, and then the current heap and stack, which is pretty useful for visually seeing if you have a memory leak, if you've forgotten to free some memory or anything like that. But honestly, this one is pretty glitchy. It was kind of difficult to get a working screenshot of it because I haven't really worked on it that much and it does have a lot of bugs. But hey, that's what it looks like. So we've talked about processes plenty, and honestly, there's a lot of other stuff that I haven't even bothered implementing yet. But since I haven't really done that, I can't really talk about it here. So we're going to leave this video here, and next time we will be talking about input, which is another thing that was quite frustrating to implement, but once you actually understand what you're doing, is somewhat simple. So we will talk about that next time.